Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's show is space debris and what are we doing about it? Here to tell us about what we are doing about it is Adam Kall from Kall Morris Incorporated. And Adam, welcome to the show.
Thank you for having me. Excited to be here.
Now, before we get into the meat and potatoes of what your company does, tell our viewers a little bit about yourself and how the company got started.
Absolutely. The company got started back in 2019 when myself and my two co-founders, Austin and Troy, all came together excited about a future of space, a future in space and working in space. I had been excited since I was a junior in high school in physics class when I decided that the section on friction was just no fun, and I wanted to work in an environment without friction. I did not realize how much more difficult that was going to be, but mistakes of the past. So the three of us are together. We'd all graduated college a couple of years ago, and decided, okay, we want to work in aerospace for the next 40 years, for an entire career. What could we do? And as we looked into that, we realized a kind of uncomfortable truth, which was space debris was a problem. It was a growing problem, and the estimates for how long we had left to solve it were shorter than the career we wanted to have in space. And so we looked at this and realized we could start a great career and after 15 years have to go find other jobs because you just couldn't work in space anymore because the debris made a big problem of everything. So we decided in that moment, let's try to start a company focused on solving that problem. Let's have that be our first foray to solve this problem so that space continues to exist as a profitable area to benefit the people of Earth and that us and our future children could have long careers in that industry.
Well, it sounds like a very admirable goal to strive for. It's not something that the average person thinks about, that there's, junk up there. So, why does the space sustainability matter?
Well, I think it's an important conversation because sustainability on Earth is typically described in terms of externalities. So you have, garbage in the ocean, and we all know that we should clean that up. We all know that it doesn't belong in the ocean, but while it's there, it's kind of floating on the surface and it's over the horizon, and we really don't think about it. Up in space, it's a bit different. That debris, because it's in orbit, is moving at orbital speeds, and every orbit crosses every other orbit at least 2 points, and so you end up in this dynamic where each piece of debris is an exponential increase in the risk to every satellite that we have in orbit. And this risk, if it comes to fruition where they collide, it's not just that satellite is gone. It's fragmented into now thousands of more pieces of debris. So it's a sustainability problem where the problem is coming at us, it's coming after us, and if it wins, if we don't do something about it, it's going to make the problem even worse. This kind of exponential increase in how bad it gets.
So, this would get in the way of sending future spacecraft and missions to outer space.
In fact, it already has. In the past, we used to have launch windows that were several hours long. So if the rocket on the pad had some glitch, they would just pause for a little bit and then decide, okay, we'll launch it now. But now we're in a situation where there are these clouds of debris that are going around, where a launch might have to be delayed, not for any problem with the rocket, but because the path isn't clear. And if the debris keeps getting worse and worse, that could get so much worse that suddenly the rocket never launches at all. It just stays on the pad because there's no safe path to get out of our atmosphere and onto, Mars and Jupiter and the future planets of the solar system.
Now, just so that it helps me understand as well, but our guests, I get the mental impression that we have this giant belt of debris around the Earth, kind of like Saturn has its rings.
Yes, but not. We have many of them, and they're crisscrossing each other, and the biggest one is actually at sun synchronous orbit. So all of the imagery that we get of Earth, these beautiful Google Maps images, that's a really important orbit to be in because you can make sure that shadows are the same every day. So if you take a picture of, Los Angeles at 10 a.m., you want to take another picture of Los Angeles at 10 a.m. so that the shadows are in the same place and you can compare them. So you need to be in this very thin line and very thin orbit. And because we've been doing that now for decades, there's a lot of debris in that orbit. So we have a whole cloud, there's a lot of debris, but as you're looking at it, really 98 degrees inclination is in a really bad spot right now. It's kind of the first orbit that has been handed over to debris as like this is a problem.
Okay, well, that's good to know. Uh, Tell us a little bit about KMI's mission and your role in this space sustainability.
Absolutely. So we only were able to start the company and be aware of this problem because many groups have gone on the difficult task of tracking this debris. So there's thousands and thousands of these objects, and there's many great groups on the ground that are tracking it to identify where it is. And that's the main approach right now to avoid disaster is saying if we know where the problem is, we can avoid it, and we'll just keep doing that forever. If you look at the data, if you look how it's growing, there becomes a critical point where you can no longer avoid the problem. And so we said what is needed is a solution to physically grab the debris. At some point, somehow, we have to grab onto this debris and move it to a new, safer location. And so that's what we set out to do, develop that technology that would allow us to physically interact and grab hold of a piece of debris.
And move it out of the way, so to speak.
So to speak.
Yeah.
If you're in space, you're always in the way somehow. And so our ambitions are either bring it down to atmosphere so it can safely re-enter, or bring it to some kind of orbiting space station so it could be reused for a future purpose.
Now, is there an international collaboration tied in with this?
There is in a sense. The problem of space debris is an international one. If I have a piece of debris, it's not going to differentiate between friend and foe. It is a problem to everyone in orbit. In that same vein, though, because it's a problem to everyone in orbit, there's a bit of a bystander effect of people don't want to be the first one to take on that responsibility. So we have to be careful and choose our battles, but something that we identified early on is not all debris was made equally. If you look at the distribution of objects and you're really smart about how you analyze it, you recognize that some debris is a really bad problem for a specific customer, and that's your first target. If you can remove those objects, you lower the overall risk of debris in orbit, but you specifically help one customer who is willing to pay for it. So there's a nice balancing act here between the technology but also the business case to bring the solution to fruition.
So I would imagine that the majority of the debris up there would be American and Russian.
American, Russian, and Chinese. Those are the big three. Europe has been fairly responsible with its orbital debris and doing a good job, but there's still a sliver that's their responsibility. And then other launchers, but really anyone who's put anything into space, there's a good chance they still have some debris left over. I believe the only country right now that has a clean record, a space country, is New Zealand, and they're particularly proud about that fact.
Oh, good, good. Is there an international agreement that we have that helps govern this so we're just not pointing fingers at each other?
There is an international agreement that governs it. The term helps is a little bit interesting. The agreement is from the Cold War where we said, don't touch our stuff. So that does present a problem for companies like ours where we know this Russian rocket body is a problem. It's been inert for 40 years, it needs to be moved, but that's definitely a challenge that we have to overcome of getting permission to go remove that debris because we're US, they're Russian. Are we allowed to grab the debris? According to the treaty, not yet. But there's a lot of forces right now in governments and international bodies that want to revise these agreements to allow for these kinds of benefit for all mankind operations.
Sounds like a plan. Can you tell our audience about REACH?
Right. So when I was saying develop that technology to physically grab an object, that is manifested as our reach end effector. It's this very fascinating design where we looked at the way that an octopus grabs onto objects. Because an octopus swimming in the ocean doesn't need to know the shape of the object beforehand or even really prepare in advance. It can just move its tentacles and wrap around the shape. So we designed an end effector that is that same design of these 8 tentacles that unfold to match the shape of the target. And if it's small enough, wrap all the way around. But if it's a bit larger, we can actually adhere to the side instead.
And what are your particular technologies to do that? Do you hit giant suction cups?
Well, when you're in space, the approaches you would normally take of suction, magnets, or a sticky adhesive, they all present a certain problem. With suction, you're already in a vacuum, so you can't really vacuum onto something else, so that doesn't work for us. For magnets, most of the objects we're grabbing are not magnetic, or at least we can't guarantee that they are magnetic, so that's not a great approach for reliability. And then for any sticky adhesive, it's always a little bit liquid, so you end up sublimating in the vacuum of space where it just boils off and becomes this hard, crusty surface. So the approach we took was actually inspired by another animal, the gecko. If you're in a climate that's appropriate for them, you might find these lizards climbing up your windows or on your walls, kind of defying gravity. And the way they do that is their paws, their little pads, have these wedges that when they apply a shear force, the wedge bends backwards and makes a very tight surface connection to the object it's holding onto. This is so tight and so close that the atoms in their pad start sharing electrons with the atoms in the wall. And it kind of confuses the physics where it's like, is this the same object? And you get van der Waals forces that adhere them together. Not super strong, but in space it's strong enough for us to hold onto an object and start moving it.
Wow. So again, it's not suction because you can't create suction in a vacuum, but oh, that's an interesting technology. It's kind of like Velcro in a way, but not really.
In a way, the application and possibly the revolution that Velcro caused in consumer products is similar to what we might see in space. And so it's exciting that the gecko part of this technology has actually been tested on the ISS several times in the years past. And now the full reach assembly has also been tested in the ISS under the control of KMI and our current mission on board.
Interesting. Interesting indeed. Well, we're going to have to take a quick break. If you have a question, you can send us an email. The address is down there at the bottom of your screen. And we'll be right back after Term of the Month with Stephen.
Thanks, Don. The term of the month is Cosmic Noon. The cosmic dark ages started at 370,000 years after the Big Bang. When stars formed, clouds of neutral hydrogen were ionized, leading to the epoch of reionization. That's when the universe became transparent to normal light. The cosmic dawn refers to when the first galaxies emerged from the cosmic dark ages. This happened at something less than 1 billion years after the Big Bang. Cosmic noon followed the cosmic dawn and extended through the first 2 to 3 billion years of the universe. Cosmic noon studies include looking at the growth of early black holes and galaxies. The James Webb Space Telescope's fourth cycle comprises 274 programs for a year of observations. These cosmic noon topics are a big part of these programs. Looking back toward the start of the universe requires excellent resolving power and long exposures. That supermassive black holes are at the centers of all big galaxies was learned in the 1970s. Observations since then have led to a theory of supermassive black hole growth in the most recent 7 billion years. Formation and growth in the first half of the universe remains largely a mystery. Hubble Space Telescope and James Webb Space Telescope observations have found seeds of the first supermassive black holes in the early universe. Some are over 1 billion solar masses, much larger than expected. Proposed explanations are black hole formation by direct collapse of massive clouds, gas clouds, or from primordial black holes that may have existed shortly after the Big Bang. And that's the term of the month, Cosmic Noon. Back to you, Don.
Thanks, Stephen. We're back with our guest, Adam Kall from KMI, that deals with the problem of space debris. Now, talk to us a little bit about the excitement of working in space technology.
Absolutely. So as a kid, as a younger lad, I was so fascinated by space because it really pushed the boundaries. I had always known, even when I was little, I had immediately looked up what did we learn from space and what technologies, and I learned, oh, my tennis shoes were first developed for the space shuttle, and I learned, oh, this technology and that technology. But it was fascinating how that was never the purpose. They didn't set out to design an Earth-based technology in space. It was that space requires the utmost in terms of ingenuity and technology advancement to face the challenges that are up there. And when we do that, when we achieve these incredible results, the what we can learn and put back on the ground is always unexpected and always beneficial. And so that was kind of the beauty of this industry was we are on the cutting edge, but it doesn't mean that it's just for space's benefit. We're learning things every day that can be applied on the ground as well.
It's sort of like the old story of how they developed Tang.
Yes, exactly. Although a bit of a marking there, but even there, the ambition of what would be a product that we would use in space immediately then developed into a favorable product here on the ground.
Now, how did your company journey from this idea to actually being a player in space?
Well, it was certainly a long journey and by no means a straight path. The first thing was me and my two co-founders came together. We looked at ourselves. We said, we've got experience, we've got gumption, we've got all this drive, which means we definitely don't have enough to do this by ourselves. We need to create a company and we need to hire on other very smart individuals to help us on this journey. In no way is this the result of just my efforts. There's a team of 20 full-time staff who've been behind this project, many of them for several years now, helping make this dream become a reality. And all of us came together, sharing our ideas and sharing our diversity of thought to say, what would we do to accomplish this main mission and how would we achieve it? And that journey has honestly probably been the most rewarding part of seeing these brilliant individuals be given a very difficult problem and each come up with their part of the overall solution.
Yeah, teamwork is definitely the name of the game. Now, what's it like to work with NASA?
Working with NASA is really a kind of pristine opportunity. I actually got my first opportunity as a sophomore in college when I was awarded a NASA internship. So I got to spend the summer out at Goddard Space Flight Center, learning from some of the experts, seeing the James Webb Space Telescope when it was still in the clean room, getting prepared over there. And that was a really great experience for me, but it also taught me how NASA was full of these brilliant individuals that then had to deal with Congress. And regardless of what party is in Congress, you have to deal with the whims of politics and the whims of is this mission in favor or not? And it just seemed a little bit stressful. Working now as a private company with NASA, it's really beneficial because we can bring a kind of sense of stability to what they're working on. The mission that we're doing on the ISS is involved with the Astrobee robots, and that team has really been able to work alongside us knowing that we aren't going to suddenly change our minds and say, oh, never mind, we're not interested in it. You can keep our prototype. We are so dedicated to this mission, and they can work with that stability to really spread their wings and do an amazing job supporting our mission.
You mentioned Astrobee. What's that?
So Astrobee is this incredibly cute set of robots that they have on the International Space Station. They have these technically called impellers because they suck in air on the station to move themselves around. And the idea is that they can pilot themselves to autonomously survey the station and find lost tools or check for leaks or do other activities rather than call an astronaut over. We were able to design a mission that fit into one of these Astrobees. So while it's flying around the station, it now has a reach end effector on the top that it can use to go and grab an object.
Sounds like a space age robot.
That is what we have turned it into, but it is many things. It is that and much more. The Astrobee program has been a delight to work with, and seeing their other experiments as well really shows that ingenuity of space that we've come to love.
Now, what are KMI's next steps? I mean, how does space debris removal work?
Well, so we had our end effector technology, and there were several tests that we could do on the ground. So we were able to test it in a vacuum chamber to know that it would survive the vacuum of space. We could test it in a thermal chamber, which really is just a fancy word to say an oven, that would showed us that it would work in the temperatures of space. But getting it up onto the International Space Station was really the final test to show it could work in the microgravity of space. When you think about grabbing something, when you think about picking up something, you're thinking about it in the reference frame of the Earth, where you're stationary and on the ground, and it all makes sense. And suddenly in space, those rules are thrown out the window and you have to deal with a whole new set of rules. So, confirming it worked on the station was the final hurdle to give us the confidence to move forward with a full mission. So, that's the next part. We designed Reach to solve a problem that hadn't been solved before. So, it's all new technology and all new kind of approach. The rest of the spacecraft, though, we designed with off the shelf components. We knew the satellite industry was thriving and that people were making batteries and solar panels and radios. And so rather than try to design that all ourselves as well, we worked off of those kind of the shoulders of giants to take that technology and combine it into a spacecraft that would fit our missions and then put our new technology on the front of it.
So you could go to the spacecraft hardware store and build your craft.
Absolutely. And with that, we get to do it faster and cheaper, and we still have a spacecraft that is fully capable, made of parts that have already been in space and already tested. So it's a very nice advantage and one that I'm excited about because we're not the only ones who can take advantage of it. Anyone that starts a satellite company today can take advantage of this catalog of ready-made parts to go and assemble it and do their mission.
Yeah, it saves a tremendous amount of time and cost not having to test for the environment that it's going to be in.
Absolutely.
Now, what would be the potential for gathering the debris? How would we use it? I mean, once it's gathered.
So the exciting part about objects in space is everything up there went through a rocket launch, right? It went through that exciting moment of seeing this giant tower of steel and fuel and a column of flame rise into the sky, which means it's in orbit and that's what makes it valuable. A kilogram of aluminum here on the ground, I might be able to buy from the hardware store, not the satellite hardware store, just the normal one. I might be able to buy a kilogram of aluminum for $1. But if it's in space, it's now $5,001 because you add the cost of getting it up there. So when we go up and grab space debris, some may call this junk, but it's actually the components that we can recycle and reuse in order to create some new structure in space, a new space station, a new spacecraft, or just repair the other satellites that are up there. The fascinating thing about satellites is, if you have a key component fail, you might call it debris, but 95% of it is still functional. So if you take one of those satellites and disassemble it, you can go repair 19 other satellites that had their one component fail and need replacement. So it's an exciting future where we get beyond this launch a mission and hope it works until it doesn't.
Well, that would be great. Yeah, to use what's there. It's like the missions to Moon and then eventually to Mars, where, find water, find other minerals and substances that we can use that are there instead of having to drag it up with us at such tremendous cost.
Yeah, we call it the void of space, but for better or for worse, around Earth, that void is now rich in resources that we put there. So there's definitely an opportunity to take that as an advantage and as a resource rather than just a problem. Certainly is, but there is a silver lining that we can make use of once we solve that problem.
In the couple of minutes that we have remaining, um, how are you reaching out to students and educators about your program?
Well, I think one of my favorite things to do is to go to classes, especially here in our local area, but even to talk remotely, like we're doing now, with other groups around the country where you can introduce to them young, some of these are in junior high, some of them in high school, this idea that they too can work in space. And it's something that I think was maybe a little lost on us. I know growing up, it felt like in order to work at NASA and work in space, you truly had to be the best of the best, and only the very elites got in. But the reality is that space takes all types. On our team, we of course have orbital dynamicists and astrophysicists and aerospace engineers and all kinds of technical folks. But we also have artists and dancers and other folks that have their own skills and their own traits that they have found a way to apply to space. So engaging with these students and telling them you don't need to give up on your dream and go like math. You can take what you like and find a way to apply it to this massive industry, because that's really what space represents, is a broad scope of need and a growing scope of opportunity.
Well, it sounds like there's, as you say, a lot of opportunity here for a lot of different people as we move forward. Adam, I want to thank you for taking the time out of your schedule today to talk with our audience about what you and your company do in space.
Absolutely. Happy to spare the time and happy to have the discussion. It's always a joy.
We would ask our viewers to please check the club website. The address is down there at the bottom of your screen. And coming up next to close out the show is Stephen with What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for April 2025? The days are getting longer or shorter as we head from the equinox to the solstice. That's the winter solstice in the northern hemisphere and the summer solstice in the southern hemisphere. Now, the first phase of the moon is the first quarter, and that happens on the 4th of April. The full moon is on the 12th, and we have apogee on the 13th, so this is a smaller than usual full moon. Not that you'd notice. Third quarter is on the 20th, and new moon is on the 27th. Then we have Mercury, Neptune, Venus, Saturn, Pluto on the 30th of April, shown here at sunrise. Everything is better at the end of the month. Mercury is in Pisces and rises from a half hour to 45 minutes before sunrise. Max western elongation, when Mercury appears to be farthest from the sun, is on the 21st. That may be your best bet. Neptune is in Pisces and rises from a half hour to 1.5 hours before sunrise. Venus is also in Pisces and rises from 2 hours to an hour and a half over the course of the month before sunrise. Saturn goes from Aquarius to Pisces and rises from a half hour to, well, a half an hour before sunrise over the course of the month. Pluto is in Capricornus and rises from 2 to 3.5 hours before sunrise. Then we have Mars, Jupiter, and Uranus, shown here on the 1st of April, at sunset, plus a little bit, and everything here is best at the beginning of the month. Mars goes from Gemini to Cancer and sets from 3 to 3.5 hours before sunrise. Jupiter is in Taurus and sets 6 to 7 hours before sunrise. Uranus also is in Taurus and sets from 3.5 to 1.5 hours after sunset. Now, consider this. A hole in a black sock is a black hole. These suck in other socks in the dryer. After a Google years, they are emitted as stocking radiation. And that's what's up in the night sky for April 2025.